Welcome to the CompTIA A+ Prepcast presented by baremetalcyber.com. The motherboard is the foundational circuit board that connects all critical components of a computer system. It serves as the central platform that integrates the processor, memory, storage devices, and peripheral interfaces into a cohesive unit. Every major data pathway in a system runs through the motherboard, allowing communication between the central processing unit, also known as the CPU, and the rest of the computer. In addition to providing structural support for hardware, the motherboard also houses expansion slots, power connectors, and header interfaces for additional components and external controls. Selecting a motherboard requires attention to its form factor, socket type, and compatibility with desired features to ensure that all other parts of the system will integrate correctly. The ATX, or Advanced Technology Extended, form factor is the most widely adopted motherboard standard for desktop systems. Its standard dimensions are 12 inches by 9.6 inches, providing ample space for features and components. ATX boards typically offer full support for expansion, including multiple PCI Express slots for graphics or network cards, and multiple memory channels for DDR modules. The size of an ATX board allows it to accommodate a comprehensive set of connectors, headers, and chipsets, making it ideal for systems that require high performance or extensive upgrade options. This form factor remains a common choice for gamers, power users, and general desktop builds that do not face space constraints. Micro ATX, often abbreviated as MATX, is a smaller version of the ATX form factor, measuring 9.6 inches square. This reduction in size results in fewer expansion slots, typically providing 2 or 3 PCI Express slots instead of the 4 or more found on full-size ATX boards. However, micro ATX boards usually support the same central processing units and memory types as their larger counterparts, making them a cost-effective option for standard computing needs. Their compact dimensions allow them to fit into smaller cases, which is advantageous for space-saving builds, such as office desktops or budget gaming systems. This form factor balances functionality with reduced size and cost. Mini ITX is an even more compact motherboard form factor designed for space-constrained environments. These boards measure 6.7 inches square and are often used in small form factor systems or home theater personal computers. Mini ITX boards typically include only one PCI Express slot and 2 memory slots due to their size limitations. Despite these constraints, Mini ITX boards offer impressive features such as integrated Wi-Fi, Bluetooth, and audio, making them suitable for streamlined builds. They require specialized cases and cooling considerations, but are popular for minimalist designs where physical space and power consumption are limited. When comparing ATX, Micro ATX, and Mini ITX motherboards, several trade-offs emerge regarding expandability, airflow, and spatial efficiency. ATX provides the greatest expandability and is suitable for high-performance builds with multiple add-in cards and large memory footprints. Micro ATX reduces the number of available slots but remains highly compatible with standard hardware. Mini ITX sacrifices expansion for minimal size, which can limit upgrade paths. Each form factor also varies in mounting hole placement, so it is essential to ensure that the computer case supports the chosen size. Using the wrong case can lead to incompatible mounts or insufficient space for components. Motherboards include a variety of connectors and ports necessary for powering and interfacing with other components. The primary power connector is the 24-pin ATX connector that supplies electricity to the board itself. In addition, there is often an 8-pin connector specifically for the CPU's power needs. Data connectors include SATA ports for storage devices, M.2 slots for high-speed solid-state drives, and internal USB headers for case I/O ports. Along the rear input and output panel, motherboards provide a range of ports, including USB, Ethernet, audio jacks, and video outputs such as HDMI or DisplayPort. Knowing these connection types is important for ensuring device compatibility. A key determinant of motherboard capabilities is the chipset it uses, which controls communication between the CPU and other components. The chipset defines what features the motherboard supports, including the number of PCI Express lanes, available USB ports, storage interfaces, and overclocking functionality. Different chipsets support different configurations and performance levels, which is critical when selecting a board for specific tasks. For instance, high-end chipsets may enable memory overclocking or multiple graphics card support. Intel and AMD each offer their own chipset families, and choosing a motherboard with the appropriate chipset is essential for getting the desired functionality and performance. The BIOS, or Basic Input-Output System, and its modern replacement UEFI, or Unified Extensible Firmware Interface, provide low-level control over motherboard settings and initialization. These firmware systems reside in a non-volatile memory chip located on the motherboard. During startup, the BIOS, or UEFI, initializes hardware, runs diagnostic checks, and hands off control to the operating system. UEFI includes more advanced features than legacy BIOS, such as graphical configuration menus, mouse support, secure boot options, and support for large storage devices. Understanding the role of BIOS and UEFI helps explain how hardware settings are configured before the operating system loads. CPU socket type is a crucial specification that determines which processors a motherboard can support. Each socket design is tailored to a specific family of CPUs and must match not only the brand, such as Intel or AMD, but also the generation and architecture. Intel motherboards typically use LGA or land grid array sockets, where the pins are located on the socket itself. In contrast, AMD often uses PGA or pin grid array, where the pins are found on the processor. The AM4 socket is an example of AMD's approach. CPU sockets are not interchangeable across vendors or generations, making it essential to confirm compatibility before purchase or installation. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Modern motherboards often include a wide range of onboard components designed to reduce the need for additional expansion cards. These built-in features typically include integrated sound cards for audio output, Ethernet ports for network connectivity, video outputs for systems using integrated graphics, and Wi-Fi modules for wireless access. These integrated components are sufficient for the needs of most users and contribute to cleaner builds with fewer cables and cards. If a user prefers to use a discrete component, such as a dedicated sound card or network adapter, the corresponding onboard feature can usually be disabled in the system's BIOS or UEFI firmware to avoid resource conflicts. Expansion slots provide the capability to add specialized hardware to a computer system. The most common slot type in use today is PCI Express, or PCIe, which comes in various lane configurations such as X1, X4, X8, and X16. These designations refer to the number of data lanes and influence the total bandwidth available to the installed card. Graphics cards typically use the X16 slot due to their high data throughput requirements. Smaller cards, like sound adapters or network interface cards, may use X1 or X4 slots. Legacy PCI slots, which predate PCI Express, may still appear on older motherboards but are no longer standard on modern systems. The motherboard also includes a small battery that plays a critical role in system stability and configuration retention. This battery, usually a CR2032 lithium cell, powers the CMOS memory, which stores BIOS settings, including system time and hardware configuration data. If the battery fails or is removed, the BIOS settings may reset to default values, potentially causing boot issues or hardware misconfigurations. Performing a CMOS reset, either by removing the battery briefly or using a dedicated jumper on the motherboard, can help troubleshoot certain startup problems. Battery replacement is generally required every few years to maintain system configuration stability. Headers are specialized connectors on the motherboard used to link case components and peripheral interfaces. Front panel headers control basic system functions like the power button, reset switch, power LED, and hard drive activity light. USB headers connect to front panel USB ports, while audio headers support headphone and microphone jacks on the front of the case. Each header has a specific pin layout, and proper orientation is required for functionality. Misaligned connectors can result in non-functional controls or ports, which can complicate diagnostics and usage. Understanding the location and purpose of each header is critical during system assembly or troubleshooting. Motherboard installation involves precise mounting procedures to ensure electrical safety and mechanical stability. The motherboard must be aligned with the mounting holes in the computer case and secured using screws and brass standoffs. These standoffs elevate the board above the case surface, preventing unintended contact with conductive materials that could cause electrical shorts. Each screw must be tightened just enough to hold the board in place without causing flexing or damage. Improper mounting, such as missing standoffs or over-tightening screws, can result in instability, failed boots, or even permanent component damage. Diagnosing motherboard-related issues often involves observing visual or audible indicators during the power-on self-test or P-test. Beep codes emitted by the system speaker or LED codes displayed on the board can indicate problems with memory, CPU, or other components. Some motherboards include diagnostic displays or LEDs that show error codes to guide troubleshooting. Common problems include systems that fail to boot, display no video, or power cycle repeatedly without completing startup. Isolating faults may involve removing non-essential components, testing with known good parts, or using reset procedures like clearing the CMOS. Voltage regulator modules, or VRMs, are critical for ensuring stable power delivery to the CPU and memory. These circuits convert the 12-volt input from the power supply into the lower voltages required by modern processors. The number of power phases and the quality of the VRM design affect a motherboard's ability to maintain stable operation, especially during overclocking or under high-performance workloads. More power phases typically mean better voltage regulation and thermal efficiency. Many motherboards include heat sinks or even active cooling systems over the VRMs to help dissipate heat and maintain component longevity. Motherboards are designed for different market segments, including consumer, gaming, and workstation categories. Consumer motherboards aim for general-purpose use, offering standard features at an affordable price. Gaming motherboards typically include enhancements such as improved VRMs, multiple GPU support, customizable RGB lighting, and reinforced slots. Workstation motherboards focus on reliability and precision, often supporting ECC memory, additional storage interfaces, and specialized chipsets optimized for professional software. Understanding these distinctions is important when evaluating what board type best matches a given computing need or use case. Motherboards are packaged and shipped in materials designed to prevent electrostatic discharge, or ESD. Typically, the board is sealed in an anti-static bag and cushioned with foam or cardboard padding. When handling a motherboard, it is essential to hold it by the edges and avoid touching the electrical contacts or circuitry. Grounding oneself with an anti-static wrist strap or by touching a grounded metal surface helps prevent damaging components with static electricity. These precautions are especially critical during installation, as ESD damage is often invisible but can lead to component failure. For exam preparation, it is vital to recall the size differences between the ATX, Micro ATX, and Mini ITX form factors and how each affects system design. Recognizing motherboard features such as CPU sockets, RAM slots, power connectors, and onboard ports is essential for identifying components in exam scenarios. Understanding how different chipsets influence features, how to install and secure motherboards properly, and how to troubleshoot related issues are all part of a well-rounded knowledge base. This foundational knowledge ensures you are prepared to answer questions on system architecture, compatibility, and component function accurately. Thank you for listening. Please visit baremetalcyber.com for more cybersecurity information, podcasts, books, and more.